we're going to start looking at applications of systems of equations, and one that really shows up in calculus, particularly in Calc 2, is the idea of partial fraction decomposition. Long words, long confusing phrase, I get it, but the main idea is this. In your beginning algebra courses, you've probably seen and learned how to add and subtract rational expressions. Now, rational expressions are just fractions with polynomials. We've learned about those in the past. And so you can add rational expressions, something like x plus 3 over x plus 1 plus x over x minus 2. And you can add those by getting common denominators. Multiply the top and bottom by x minus 2 here, multiply top and bottom by x plus 1, distribute. Once the denominators are the same, you can combine the numerators together and get a result. Well, what we're going to do is basically the reverse of all that, okay? So you're going to start with the end result, which is a single fraction, and you're going to split it up into these options, okay, these types of functions. Essentially smaller fractions that are going to be easier to work with than a more complicated single function or rational expression. And so just given that as your basic idea, partial fraction decomposition is that idea. You take a complicated rational expression, long, you could have quadratic on top and a quintic on the bottom or something, you've got larger polynomials involved, and you're breaking it down, decomposing it, into multiple smaller fractions. And so we're going to call this partial fraction decomposition, this idea of breaking a more complicated fraction into smaller, more simple ones. Now, to do that, I really need to define, I've got 6 terms here, 6 things to define, and you're really going to need to know these definitions. They are going to show up. I'm going to be saying them a lot. You're going to see them in your book and on my math lab and the homework on the test. It's really good to know them. I wouldn't test you specifically on a definition, but you're going to need to have these as part of your regular vocabulary, moving forward. And so the idea of a proper rational expression, well, you guys, I'm sure you know what a proper fraction is. A proper fraction is something like 2/3 where the top is smaller than the bottom. In a similar way, a proper rational expression is one in which the degree on top is smaller than the degree on the bottom. Okay, so the degree of the numerator, that's the top, is less, put it over here, than the degree of the denominator. Okay, so you might have, a proper fraction, you might have something like x plus 2 over x squared minus 9. I have degree 1 on top, degree 2 on the bottom. As long as the degree on top is smaller than the degree on the bottom, it's a proper rational expression. Okay? Now, contrary to that would be an improper rational expression. And just like improper fractions, an improper fraction might be something like 7/4, where the numerator is greater than the denominator. Also, something like 3/3, that would also be an improper fraction when they're the same. And so an improper rational expression is one in which the degree of the top is greater than or equal to that of the bottom. Okay? So the degree of the numerator is greater than or equal to the degree of the denominator. Okay, so that would be the other possibility, all right? So it's all based upon the degree of the polynomials. All right, now for a we have some interesting things about polynomials. We've talked a lot about polynomials and their factors. And here, we're going to talk about repeated versus non-repeated factors. A non-repeated factor is a factor of a polynomial in which the power is 1. We've called those multiplicities in the past, all right? And so here, it's a factor of a polynomial whose power is 1. It's non-repeated, right? So something like x plus 2 to the 1 power is a non-repeated factor. A repeated factor is one where the exponent is greater than 1. So it's a factor of a polynomial whose power, or we could say multiplicity. Multiplicity is more for the 0 of the polynomial, but I'll just say power for now. Whose power is, let's move it over here, greater than 1. An example might be something like x minus 3 raised to the 4th power. Anything greater than 1 as the power, obviously, okay? And in fact, another example, this one is one that may not appear to be an example, but it is. How about x minus 0 squared? That's a repeated factor, right? It's equal to just x squared. And so it has a power. It has a power that's not 1, okay? It's a factor with a power not 1. Okay, now, the next set of definitions is reducible versus irreducible. All right, so a reducible polynomial is one that can be factored into smaller polynomials. Okay, so it's a polynomial that can be factored into polynomials. In fact, I'm going to say polynomials with lesser degree. And I guess that's kind of a given, but you know, something like x squared plus 5x plus 6, that's an example of a reducible polynomial because it factors into x plus 3 and x plus 2. All right, so it's reducible. Take a polynomial and reduce it down to its factored form. An irreducible polynomial, on the contrary, is one that cannot be factored out. It's prime, essentially. Prime over the integers. So it is a polynomial that is prime over the integers. In other words, I can't factor it using integers. It may be the case that you could factor it using irrational numbers, something like the square root of 2 or something. An example here might be something like, x squared, plus 5 or something like that. Now, x squared plus 5 doesn't factor, okay? Now, it technically does if you allow it to use complex numbers. You could use plus or minus I root 5, I think would work there, or something like that. But we're not going to use complex numbers or irrational numbers or anything like that. We want to keep these nice, so we're going to keep them to integers. So this would be an example of an irreducible polynomial, okay? So that gives you just an idea of some of the things we're going to be looking at. Now, in order to decompose a fraction, a rational expression, we're going to need to factor the denominator. That's why all this is important, to identify the different types of factors you can get. And then we're going to create functions or other rational expressions based upon those factors in the denominator, Okay, so in the next couple videos, we'll go through how that works.